it loud enough? Okay. So, good afternoon. Thanks for coming. My name is Bob Saia, and I run the commercial development programs, very specifically focused on our new generation product, the geared turbofan, that's powering several of the new single-aisle aircraft. So what I'd like to do this afternoon is really give you a briefing of our overall program. But I know there's been a lot of buzz about technology, especially after some of the weekend interviews. So I thought what I would do is maybe get a little bit into technology and product to kind of put the Pratt story on the paper here. All right, so our overall objective, we launched this program in 2004. Now, our overall objective was to drop engine operating costs 20%. And it's made up of four key characteristics. Fuel, which represents almost 50% of the airline's direct operating costs today, especially in the 150 to 200 passenger market segment. Engine maintenance cost, takeoff and landing fees for noise and emissions. So those four characteristics. Fuel being the most important, representing the 50%. Engine maintenance cost is about 25 to 30%, and then landing and takeoff fees, especially if you're in Europe, can be a very dominant player. If you look at a worldwide average, it represents about 20% of this overall target approach that we took. And I want to talk all three attributes: fuel, maintenance, and then from the environmentals. So let me first start with the environmentals. All right, so if you look at what our geared turbofan product is bringing to market today relative to the two baseline power plants, the CFM56 family and our V2500. The first key element was dropping fuel. So for every gallon of fuel that we drop or that we save, we reduce about 20 pounds of carbon dioxide. All right, so to kind of roll that at an airplane level, a typical 150 passenger airplane consumes about $6 million of fuel per year. So a typical airplane flies about 2,500 flights a year. You kind of look at what that fuel is over the course of a typical operation. It's about $6 million. To then say, with our fuel savings of up to 16%, what does that mean in terms of carbon-related savings? It's equivalent to 3,500 metric tons of reduction per airplane per year. And as we start looking at carbon-related costs for takeoff and landings, it can be and will be in the future a very significant element of our focus of certainly being a good steward of the environment, but more importantly, really dropping the cost of ownership to our customers. Second element was nitrous oxide. Almost every airport in the world has some charge for nitrous, and especially in Europe or Scandinavia, they can be very significant. With our new combustor, we have essentially dropped the related nitrous oxide emissions by about 50%. When you look at the latest standard that just went into action or it went into regulation about a year ago, we still have a 35% margin relative to that. And the key element here, it just says that the engine has a long life of revenue service because we have this high margin. So we save takeoff and landing fees. At the same time, we make sure that our product has the full life capability, recognizing that we have a very high level of margin to the current regulation. And the last piece is noise. The difference, the key here in the noise, if we look at the actual decibel sound of our engine relative to a CFM56, we have dropped engine noise by 50%. So that difference is the difference of my voice today and the Sukhoi jet you just heard. That's about a 50% reduction in noise. All right, in the U.S., I often use the characteristic of a garbage disposal. If you have a garbage disposal in your kitchen, you turn that on, it's not quite as loud as a Sukhoi, but it's pretty close, all right? So, but that 50% reduction is a pretty significant reduction. When we look at takeoff and landing fees, especially in Europe, it has a significant value proposition to the airline. All right, so the combination of these three items represents about a 20% element of the overall 20% cost of ownership reduction. So roughly about 5% of that contribution, okay? The real meat comes with the next slide, which is the fuel and the maintenance attributes. So currently, the engine that's down here right now, this is the engine that you'll see in display here, is our last, or I'll say last, but it was our 8th engine that we assembled for our PW1500G certification. That engine, in its fuel efficiency, relative to today's CFM56-5B, it's powering the A320, is 16% lower in fuel consumption than the CFM. That 16% represents, on an annual savings, just under $1 million of fuel savings per year per A320 airplane that flies. That's the real significant value of lowering engine operating cost. In terms of maintenance, we really did, and I'll talk this in the next few slides, it's all about designing parts for long service intervals, so time between repairs. At the same time, managing how many parts have to be repaired or replaced. And a significant value of our geared architecture is that we remove or lower the actual airfoil count relative to, say, a CFM56 by about 1,500 parts, 1,500 airfoils. And that has a big value proposition, which I'll talk in the next few slides. So when we look at fuel and maintenance cost in combination with the environmental benefits I talked on the last slide, that represents at about $3 a gallon, about a $1.5 million savings per airplane per year. And that's really what our whole product family is targeted as, is really dropping that operating cost of the operator. So I don't normally use these slides. The next few slides is typically what I do when I go into an airline and I'm doing what I'll call engine design 101. So to talk about some of the characteristics of our engine. I wanted to talk a little bit more of it in this session because I want to talk about what we've done on technology and why is this geared architecture really driving the change that hopefully you'll see by how the market acceptance that we've had to date. So the first element is our fan. All right, now this is not a composite fan. We didn't need to make the investment, the higher cost airfoil for this size engine. When you get to the wide body engines, the composite fan blade has a figure of merit because when you look at the cost of that blade to manufacture and repair with the size, it makes a favorable trade. What we found is by keeping with a new metallic chemistry, we could keep the weight equal to a composite blade, but we can make the composite blade, the metal blade, we call it a bimetallic blade, much more fuel efficient, efficiency efficient. So what we've done with this geared architecture is this blade turns at about 1/3 the speed of today's conventional blade or our competitor's blade. So if you think about the speed of this tip up there, it's about 1/3 slower. The resultant benefit of that is over 2% in fuel efficiency associated with turning the blade slower. These big fan blades are most efficient when they turn slow. They're the best on weight, they're the best on fuel efficiency, and more importantly, they're really good on noise reduction. The noise reduction is kind of a free characteristic as we're trying to drive for fuel efficiency. If I go to what we call, some of us call this the propulsor, or the core, or the basic fundamentals of the engine, the core of the engine, it's really made up of several components. So we have a front compressor that's attached with a shaft with a rear turbine. And then we have traditionally what we call the core of the engine, which is this compressor, a combustor where we introduce fuel, and then a turbine, the high turbine. These two components are connected by a shaft. Compressors and turbines are most efficient when they when they turn quickly. The higher the speed, the more efficient they are. And the value of that efficiency is done in several ways. First of all, they're more efficient from a sense of the fuel efficiency of the design. And because they're turning at a higher speed, you can actually take parts out because you need less parts. In the case of a compressor, we're trying to compress air, so the speed helps that compression. In the case of a turbine, as this air is leaving the engine, the turbine is taking the energy of that air, trying to capture that energy, so it can drive the fan and the compressor. So the more speed that that turbine has, it needs less airfoils, just think of it as a paddle, to take the energy out of the air that's passing it. All right? So look, so speed and part count can be really key attributes if you do it right. Geared architecture really enables us to do that. And the reason for that is that we bring this gearbox, kind of a reduction gearbox. It's like the gearbox in your automobile, but it doesn't shift. It's only at first. So for every 1 revolution of this fan blade, this turbine now is doing 3 revolutions. What's the value to that? The fan likes to turn slow, about 2% in fuel efficiency. The turbine really likes to turn fast. The speed that we use for this turbine is 3 times the speed of the fan. It also reduces fuel efficiency by 2%, purely due to the mechanics of the design. So these two parts, I don't know, there's about 12,000 part numbers in an engine like this. These two parts, the fan and this turbine in the back, provide about 4% of fuel savings because of the uniqueness of this geared architecture. Now, we call this a geared architecture, and we did that because, and we actually coined that as part of a trademark, because of this unique gear. The bad thing about that is everyone thinks it's only the gear. There's about 100 unique technologies, and I'm going to talk about some of those today. And I'm going to also talk to you about what we're doing in our next step. But it's not just the gear. The gear just enables us to use this speed characteristic. That's all it does. The gear itself, other than allowing us to make the speed correlation, has no technology value. The gear that we're using in this gearbox is the same gear that we use on the engine that we power, the ATR 72 or the Q400 with our Pratt & Whitney Cannon turboprop. Same material, same design. So the gear itself isn't a unique technology other than the fact that we packaged it. So the key element of, why is this engine so fuel efficient? 2% out of the front because of the low speed, 2% out of the back because we've got higher speed, and then on all of the engines prior to our C-Series engine, you take the pressure of the air here and the pressure of the air here. Typical engine was increasing at about 35 times. In our logo, we call that overall pressure ratio. It's the pressure rise of that air, because you need pressure to make power, all right? In the case of our geared turbofan, we went on the C-Series engine to a 45 times increase. On the Neo engine, we're going to 50. When I talk to you about our next generation geared turbofan, we're going to go above 60. This pressure is really good, because pressure is a way of making that power, making the engine much more fuel efficient with that pressure. All right, so when we talk about pressure, it's important to get the absolute pressure, but because of this gear, we didn't need to do a 20 pressure rise increase in this unit only, because we got all this speed capability of this machine. So what we ended up doing is we increased pressure here about 3 times, and then we multiply that times the pressure rise of about 16 times to get to the 50. So as the air is going from here to here, when it gets to this point, it's about 3 times higher the pressure because of the capability of compressing in the first stage because of higher speed. On a conventional engine, it's only about 2 times. And then you do more pressure here because every stage is adding pressure. So we have an overall pressure rise of almost 50 to 1 on our PW1100G that's powering the A320. That is state-of-the-art industry best today for pressure.